Imagine spraying perfume. You smell it quickly because it contains highly volatile liquids, like ethanol, mixed with water. These volatile molecules readily escape the liquid state and launch into the air as a gas. In a mixture like this, every volatile component is constantly trying to evaporate. Water creates its own upward vapor pressure, and ethanol creates its independent pressure alongside it. We can calculate exactly how much pressure each liquid contributes using Raoult's law. The formula states that a component's partial pressure, Pi, is its pure pressure, Pi0, multiplied directly by its mole fraction in the solution, Xi. This chart maps out that relationship. Because the mathematical operation is a direct multiplication, we get perfectly straight lines. As the mole fraction of component 1 increases, line I rises linearly. The same happens for component 2 in line 2. Adding them together creates the total pressure, line 3, which is also perfectly linear. Because this relationship is a linear multiplication, ideal liquid mixtures always produce predictable total vapor pressures. There are no sudden spikes or drops, just a steady mathematical balance between the components. In this standard exam problem, we have a mixture of 25.5 grams of chloroform and 40 grams of dichloromethane. The most common mistake here is plugging those raw mass numbers directly into Raoult's law. You cannot use grams to calculate pressure. You have to execute a strict sequence of operations first. Step 1 is calculating the molar mass of each molecule based on their atomic weights. Then you divide the given mass by that molar mass to find the actual number of moles for each liquid. Next, you add those two values together to get the total number of moles in the beaker. Only then can you divide each component's moles by the total to find x1 and x2, the true mole fractions in the liquid phase. Now you can safely plug those liquid mole fractions into Baugh's law. Multiply each fraction by its pure vapor pressure, add them together, and we find a total solution pressure of 347.9 millimeters of mercury. But there is a second phase to this problem. The mole fraction inside the liquid beaker, Xi, is not the same as the mole fraction in the vapor cloud floating above it, which we label Yi. To find the concentration in that vapor cloud, we divide the component's partial pressure by the total pressure. Take the partial pressure of dichloromethylene, 285.5, and divide it by our total pressure of 347.9. Pause the video and calculate the vapor mole fraction. The result is 0.82. Notice that this is much higher than its liquid fraction of 0.688. Because dichloromethylene is the more volatile liquid, it escapes the beaker much faster. The resulting vapor cloud becomes significantly richer in the volatile liquid than the original mixture sitting below it. Consider a different physical system. Instead of mixing two volatile liquids, look at what happens when we mix a volatile liquid with a solid that cannot evaporate, like stirring sugar into water. This diagram shows the molecular mechanics at the surface. The green solute particles are non-volatile. They physically occupy space at the boundary layer, hoarding the surface area and actively blocking the blue solvent molecules from escaping into the air. With fewer solvent molecules able to break through that boundary, the overall vapor pressure of the solution drops immediately. This reduction has a physical consequence. Because the liquid is producing less internal pressure to push back against the atmosphere, you have to apply significantly more heat to force it to boil. This graph plots the vapor pressure of that exact solution. Since the solid solute provides zero pressure, we only have one line to track. As the solvent's mole fraction decreases, its vapor pressure drops steadily along a single straight line towards zero. Adding any non-volatile solute intrinsically handicaps a solvent's physical ability to escape. This permanently lowers the available pressure and forces a higher boiling threshold for the entire solution. We have examined two distinct systems today: mixing two liquids where both want to escape, and dissolving a solid into a liquid where only the solvent can evaporate. In both cases, the core rule of ideal solutions holds true. Vapor pressure always varies perfectly linearly with the mole fraction. When evaluating these systems, follow this exact sequence. First, define Raoult's law. Second, never use raw mass. Always convert mass to moles, then to liquid mole fractions. Third, use those pressures to find the distinct vapor phase fractions. Finally, remember that solutes lower pressure by physically blocking the liquid surface. Memorizing this specific sequence of conversions and visualizing that surface boundary will keep your logic sound, ensuring you systematically solve any calculation these chemistry exams place in front of you.